Most people think engineers are just paid to write code, follow technical instructions, or, build circuits, but that is actually a massive misconception. Think about it. Anyone can follow a tutorial when everything is working perfectly, right? But what happens when the network is crawling, the database is totally overloaded, or a user impatiently clicks a button twice? That is exactly when you need to think like an engineer. Engineers are paid to solve messy problems under real-world constraints. The code is really just one small part of that solution.
There's a huge difference in how a beginner and a true seasoned engineer approach their daily work. A lot of people treat their job as just a rigid list of tasks. You tell them, hey, build a login page or add a retry button, and they just build it. Actually, wait, let me rephrase. They just blindly build it without thinking. A real engineer doesn't accept a task at face value. Instead of just doing the task, they shift entirely to a problem focus. They ask, okay, but why do users even need a retry button? Is the payment actually failing, or is the confirmation just delayed? They have to understand the underlying problem behind the request before they write a single line of code.
Welcome to this explainer. Today, we are absolutely thrilled to explore a universal framework for turning those messy, unclear, real-world problems into highly reliable solutions. We're going to unpack the exact mindset that separates someone who merely follows instructions from someone who can design robust systems that actually survive contact with reality. Okay, let's dive into this. We're going to look at the 5 core pillars of engineering thinking: finding the root cause, the art of trade-offs, designing for scale, preparing for failure, and finally, we'll put the whole shebang together to see the mindset in action.
Pillar number 1, finding the root cause. This is all about going way beyond the surface symptom.
You see, a true engineer acts like a detective. They never, ever stop at the first visible issue. They peel back the layers to find the real reason a problem happened in the first place. A symptom is just what you see on the surface, but a root cause, that's why it happened. So if an app is slow, a really weak response is to just slap a loading spinner on it. That totally hides the symptom. But if the real root cause is a missing database index that just can't handle growing data, I guarantee you the problem will come back. Same thing if a payment fails. The symptom is the error screen, but the root cause might just be a delay in the provider's callback. If you only fix the symptom, your system literally never improves.
So, to find that root cause, engineers often use a super effective method called the 5 whys. And this step-by-step breakdown shows exactly how it works. You just ask why repeatedly. Step 1, why can't users complete a payment? Well, step 2, because the backend didn't get confirmation. Okay, why? Step 3, because the callback timed out. Why? Step 4, because the server was under massive load. Why? Step 5, because the callback endpoint performs way too many heavy database operations synchronously. And boom! Suddenly a seemingly simple UI error is revealed to be a fundamental backend design flaw. Crazy, right?
Moving right along to Pillar 2, the art of trade-offs, or as I like to call it, balancing your constraints. Here's the thing. Engineering isn't about finding perfect, magical solutions. It just isn't. It's about choosing the absolute best balance for a very specific situation. Every single technical decision has a cost and a benefit. Neither speed nor quality is universally the right choice. For instance, if you're building a quick prototype to test an idea, prioritizing speed makes perfect sense, even if it creates some messy technical debt. But if you're building a critical payment system, choosing speed over quality is disastrous. Correctness and reliability absolutely have to win out, even if it takes much, much longer to build.
And this trade-off mentality extends directly to system architecture too. A junior developer might blindly declare that microservices are the way to go because, hey, they offer massive flexibility. But a senior engineer, they look at the trade-off. Microservices add immense operational complexity. So for an early-stage product, the pure simplicity of a modular monolith is very often the smarter choice, at least until the team size and the scale of the system truly justify all that extra complexity.
All right, Pillar 3, designing for scale. Because in the real world, systems absolutely must grow.
Okay, time for a harsh reality check. A system that works perfectly for, say, 100 users might completely collapse when 100,000 users log on. To scale effectively, you absolutely must understand the difference between latency and throughput. Latency is simply how long one single operation takes. Throughput, on the other hand, is how much total work the system handles over a given period of time. You might have amazing latency for one user, but terrible throughput under heavy load. The takeaway here? You cannot fix performance until you measure both and find the actual bottleneck.
Pillar 4, preparing for failure. This is all about surviving reality.
Because, let's face it, no matter how beautifully your system scales, eventually components are going to break. It is 100% inevitable. Beginners really love to design for what we call the happy path. It's this beautiful, perfect fantasy scenario where the user enters perfect data, the network is lightning fast, APIs respond instantly, and no one ever double-clicks a button. But I gotta shatter that illusion right now. Real systems do not live in the happy path. Real systems fail. The network drops, the database crashes, users make totally unpredictable mistakes, and APIs time out. A true engineer expects failure and designs for it before it ever even happens.
So, how do we handle this? Well, one of the best ways to handle failure is a concept called idempotency. I know, it sounds like a super heavy, intimidating technical term, but it really just means that repeating the same operation produces the exact same result without causing duplicate side effects. Think about a frustrated user aggressively clicking the pay button over and over again because their network is slow. Without idempotency, they get charged 5 times. Ouch. With idempotency, the system smartly recognizes the duplicate requests and safely processes the charge exactly once. A real game changer.
Which brings us to our final pillar, Pillar 5, the mindset in action. Let's dig into the QR kiosk crisis.
Let's bring all these abstract concepts together into a super relatable, high-stakes scenario. Picture this scene. A customer scans a QR code to pay at a vending kiosk. Their banking app clearly shows the payment was a success, but the kiosk screen angrily flashes payment failed. Now, a non-engineer would just shrug, say the machine is broken, and literally unplug it to reboot it. But an engineer? No way. They immediately dive straight into the logs to investigate.
And this brilliantly illustrates root cause analysis in action. Look really closely at the milliseconds here. At 10:01:05, the user pays. At 10:01:10, the backend expects a confirmation, but it doesn't get one. So at 10:01:15, the kiosk shows a failure. But watch what happens at 10:01:30. The provider's callback finally arrives. The root cause isn't a failed payment at all. It is a delayed confirmation, and the system is just treating that delay as a failure way too quickly.
So what's the move here? How does the engineer fix this using trade-offs and scale? Well, first, they balance the immediate need by adding a pending payment state, so they immediately stop showing false failures to the frustrated customer. Then, for long-term scalability, they run automated reconciliation jobs to quietly catch those delayed confirmations in the background. And of course, they use idempotency keys so that if the network stutters, any retries are perfectly safe. They brilliantly balance the immediate user impact with long-term system reliability.
So, what does this all mean? Ultimately, the engineering mindset isn't about knowing a specific coding language or the newest flashy framework. Not at all. It is a universal framework for turning messy, real-world problems into reliable solutions. So the very next time you are handed a task, before you do anything else, I want you to ask yourself this one provocative question. What problem are you really solving? Thank you so much for joining me on this explainer, and I truly hope you take this mindset into your next big challenge.